Morning, one and all. Welcome back to the video lecture series, Probability Theory Stochastic Process. This is Dr. P Sreenivasulu. Presently, today we are going to discuss about random process spectral characteristics. So, it is very important topic. So far in the previous classes, we have discussed about this random process, the concept of voids and stationary. Any random process is said to be voids and stationary. It is going to be satisfied main two conditions. One is if we calculate the expected value of this random process x of t, it must be some constant. And whenever if we calculate this autocorrelation function of that particular random process, the autocorrelation function is independent of time. So we can say that it is a void and stationary. Void and stationary means it is the stationary characteristics it maintains. Now we are coming for the spectral characteristics. Spectral characteristics means we are going to be analyze the signal in frequency domain. So frequency domain means you need to apply Fourier transform. Now what is the problem in analyzing this random process in Fourier transform? Generally, any signal, we have the signal. If you want to see frequency domain, we can directly apply Fourier transform if it satisfies the Dirichlet conditions. If it satisfies the Dirichlet conditions, we can easily apply Fourier transform. While we're coming for this is the name itself, it is a random process. So random process means what? Random process means the amplitude is changes randomly. The amplitude is changes randomly. We don't know exactly what is the amplitude. So it is completely fails in order to it is completely failed to satisfy Dirichlet conditions. So that's why it is not possible to apply this Fourier transform for this random process. So for analyzing this random process in frequency domain, there is a difficulty. That's why instead of applying Fourier transform for random process x of t, we are going to be apply Fourier transform for autocorrelation function. So autocorrelation function is a independent of time. So we can calculate the autocorrelation function from the random process only. So the autocorrelation function gives the information about this random process only. That's why in order to in case of analyzing this x of t, we are facing the difficulty. That's why that is going to be avoided by using the analyzing of this autocorrelation function Rxx of tau. So this power density spectrum means we are going to apply Fourier transform. We are going to be apply Fourier transform for autocorrelation function. So there is a pair forms like suppose we have a signal in general point of view Fourier transform x of t. The Fourier transform is x of omega. So Fourier transform pair, we are going to write x of t Fourier transform is x of omega. What does it mean? Fourier transform of x of t is x of omega. Inverse Fourier transform of x of omega is x of t. Okay, Fourier transform of x of t is x of omega. Inverse Fourier transform of x of omega is x of t. Similarly, here also in the random process, there is a Fourier transform pair forms in between autocorrelation function and power spectral density. Now, this power spectrum is going to be represented here. There where is a represented with x of omega. This is going to be right here. Some sxx of omega. Again, omega is there. The notation is here sxx. This xxx in the why it is for autocorrelation. Already for representing, suppose if you write s of omega, again it is like a Fourier transform of s of t, like that. So for showing the significance, it is a Fourier transform of autocorrelation function. We can represent in the subscription of that whatever the letter, SXX. For a power spectrum, so we are going to be calculate here power. So that's why we are representing this is S. So Fourier transform, the pair RXX of tau Fourier transform is equal to SXX of omega. So there is no any confusion. You don't confuse here. If you have a simple knowledge on signal systems, if you have an idea about Fourier transform, now we can easily analyze this random process also by using this autocorrelation function. Again, I am recollecting the Laplace Fourier transform of x of t is equal to x of omega is equal to integral minus infinity to plus infinity x of t into e power minus j omega t into dt. That is our general formula. So based on that formula, you can just change here. What is the formula you need to write? Rx Fourier transform of Rxx of tau. Fourier transform of Rxx of tau. So if you write Fourier transform of Rxx of tau, it is equal to, we are representing the pair Sxx of omega. Sxx of omega is equal to integral minus infinity plus infinity. There it is a x of t. Here it is a Rxx of tau. Here it is Rxx of tau into e power minus j omega tau into d tau. Integral minus infinity plus infinity Rxx of tau into e power minus j omega tau into d tau. So it's a simple formula in between x of t and x of t we are not directly considering. Instead of x of t, we are considering this autocorrelation function. So it is a Fourier transform pair. You can whenever what is the Sx of omega, it is nothing but frequency domain of autocorrelation function. Now, if you want to write time domain signal, what is the time domain signal? Inverse Fourier transform of Sxx of omega. What is the formula of inverse Fourier transform of Sxx of omega? It is nothing but Rxx of tau. It is nothing but 1 divided by 2 pi integral minus infinity plus infinity Sxx of omega e power j omega tau into d omega. We are going to integrate with respect to omega here. In the frequency domain calculation, we are going to do integration with respect to tau. Whenever again we are going to reconstruct our original signal or in order to apply inverse Fourier transform, we are already the information is in frequency domain. That's why you need to apply integration with respect to d omega. It is the general Fourier transform pair. Now, you see the second definition. It is an alternate definition for calculating of this power spectrum. Is given. This Sxx of omega is equal to limit t tends to infinity, expected value of magnitude of xt of omega whole square divided by 2t. It is an alternate way of representing this, analyzing this signal. What is this xt of omega? Again, it is a Fourier transform of x of t within the interval minus t to plus t. You see here the difference between previous case and this case. Previously, we have concentrated on autocorrelation function. Whatever the formula we have obtained, that is from autocorrelation function. Here, it is instead of considering this autocorrelation function, he has considered the signal, random process signal directly x of t, but he has considered that interval instead of considering from minus infinity to plus infinity. The interval he has concentrated minus t to plus t, and he has given that limit t tends to infinity. So, if you see this formula, expected value of magnitude of xt of omega whole square, expected value of magnitude of xt of omega whole square. We know the formula of expected value of xt of omega whole square. So, divided by 2t, and that interval is depends upon that interval. Suppose it is minus t to t, 2t. Suppose it is 0 to t, t. So, limit t tends to infinity. So, there is an alternate way of finding this power spectral density. Usually, we are going to be easy point of view. It is very easy for our calculation purpose based on the autocorrelation. Now, if you see the average power of random process, if you want to see the average power of random process. So, the average power of random process, it is represented with this power, whatever the power we have, the average power is going to be calculated. Average power of random process is going to be calculated. defined as time average of second moment or autocorrelation function at tau is equal to 0. Autocorrelation function at tau is equal to 0. Now, if you see here in this formula, Pxx means power, average power, is equal to average of expected value of x square of t. So, what is this average of expected value of x square of t? Just now we have seen limit t tends to infinity. That interval, suppose it is a 1 by 2t minus t to plus t. That is the average. The meaning of average is integral minus t to plus t, and the interval is we are going to write in the denominator 1 by 2t, and we can apply this limit t tends to infinity expected value of x square of t into dt. It is directly, this formula is directly from random process, and it is also limited to minus t to plus t, because whenever we are calculating power, what is the power formula? Usually we are going to be calculate 1 by t integral 0 to t magnitude of x square of t dt. There is a formula, limit t tends to infinity. The same formula we are applying here, but it is calculated from second order. In the general formula also there is a x square of t is there. So that instead of x square of t, we are writing expected value here. Only thing, whatever the power formula, that power formula we are going to be considered here. Instead of general x square of t, here expected value of x square of t. Again, you see the average power is obtained from the random process. The average of expected value of x square of t. So what is the average? Generally, average value means 1 by t integral 0 to t. Here minus t to plus t, 1 by 2t, limit t tends to infinity dt. You are going to be right. It is. And it is going to be, it is nothing but, or if you want to calculate in an alternate way, this Pxx is equal to Rxx of tau. Already we know the formula from the properties of autocorrelation. Whenever Rxx of tau is going to be replaced with tau is equal to 0, it is nothing but Pxx. So this Pxx alternate way is, you consider that Rxx of tau formula is equal to 1 divided by 2 pi integral minus infinity plus infinity Sxx of omega into e power j omega tau into d omega. In this, if we substitute tau is equal to 0, we are going to get Pxx is equal to Rxx of 0 is equal to 1 divided by 2 pi into integral minus infinity to plus infinity Sxx of omega into d omega. It is the calculation of average power from frequency domain. Average power from frequency domain. Next, you see the properties of power density spectrum. The properties of power density spectrum. So the power density spectrum, spectrum Sxx of omega for wide and stationary process of x of t are given as Sxx of omega is always greater than or equal to 0. Is always greater than or equal to 0. So from the definition of expected value, a non-negative function. It is a non-negative function because we have considered this expected value of magnitude of xt of omega whole square. Magnitude of xt of omega whole square is a non-negative. So finally, this xx of omega, sxx of omega, definitely greater than or equal to 0. It is a one property. Next one is, this is the second property. The power spectral density at 0 frequency. The power spectral density at 0 frequency is equal to the area under the autocorrelation function. Area under the autocorrelation. Now we have a formula Sxx of omega is equal to integral minus infinity to infinity Rxx of tau into e power minus j omega tau into d tau. Suppose if we substitute omega equal to 0, it is nothing but area under the curve of autocorrelation function. So simply you consider here the formula of Fourier transform of autocorrelation function. Sxx of omega is equal to minus infinity plus infinity Rxx of tau into e power minus j omega tau into d tau. Now in this, if we substitute omega equal to 0, it is a Sxx of omega, xxx of 0 from minus infinity to plus infinity Rxx of tau into d tau. It is nothing but area under the curve. A simple property. Next one. The power density spectrum of a real process of x of t is an even function. So already We have seen this autocorrelation function Rx x of tau. Suppose this x of t is a real. Suppose the random process x of t is a real and the Rx x of tau is also a real. So what is the condition of real? What is the condition of real? Uh, what is the condition of real function and even function? Suppose it is a even symmetry, it is a even function. So x of t is equal to x of minus t, generally even function condition. So that is going to be applied for power spectral density also. Sxx of omega is equal to sxx of minus omega. So it is the even symmetry. Even symmetry means if you fold this spectrum after drawing the spectrum, whatever the from the autocorrelation function, if you apply Fourier transform after finding the spectrum, if you draw the spectrum and if you fold the spectrum with respect to vertical axis about the origin, the spectrum's magnitudes are same even though the frequencies are changes. Suppose on the right side the frequencies are positive, the left side the frequencies are negative. But coming for a y-axis, if you see the amplitudes are same, then we can say that it is a even symmetry. When it is possible, suppose x of t, random process x of t is a real, after finding this Fourier transform for autocorrelation function, then the spectrum, if you observe, the spectrum is a even condition. Now, if you see this is a formula, now you write down Sxx of omega is equal to what is your formula minus infinity to plus infinity Rxx of tau into e power minus j omega tau into d tau. In this, omega is replaced with, suppose if you replace omega with minus omega, so wherever you have a omega, if you replace with minus omega, it is going to be that exponential term e power minus j omega tau is going to be changed e power j omega tau plus. Now, if you replace this tau with minus tau, if you replace with tau with minus tau, tau with minus tau. Now, again, that formula integral minus infinity plus infinity Rx x of minus tau into e power minus j omega tau into d tau. So, from the autocorrelation properties, we know Rx x of tau is equal to Rx x of minus tau. Rx x of tau is equal to Rx x of minus tau. So, from that, whenever it is an even condition, it is a real, Rx x of tau is equal to Rx x of minus tau. So finally, if you see, it is this xx of omega is a even function. Xx of omega minus omega is equal to sxx of omega. So it is a even function. So xx of omega next property is always real function. Is always real function. Now you see this xx of omega is obtained from expected value another way limit t tends to infinity this expected value of xt of omega whole square by 2t since the function magnitude of xt of omega is a real function. So you definitely it is a real function because we are considering this magnitude of xt of omega, so it is always a real. That's why this xx of omega is always a real. Okay, now you see the next property, the if Sxx of omega is a power spectral density, usually it is called power spectral density. Power spectral density of the wide sense stationary, WSS means wide sense stationary random process x of t, then we are going to be write 1 divided by 2 pi integral minus infinity plus infinity Sxx of omega d omega is equal to 1 divided by 2 pi integral minus infinity plus infinity Sxx of omega d omega nothing but generally Rxx of 0. It is equal to average value of expected value of x square of t. It is nothing but a power. It is nothing but a power. So you see here average power, average mean power. If you see this formula, Rxx of tau is equal to average value of expected value of x of t into x of t plus tau. Now, it is also we are going to be right 1 divided by 2 pi into integral minus infinity plus infinity Sxx of omega into e power j omega tau into d tau. Now, if we substitute this tau is equal to 0, a into average value of expected value of x square of t is equal to 1 divided by 2 pi into integral minus infinity plus infinity Sxx of omega into d omega. It is nothing but area under the curve of Sxx of omega, Sxx of omega. So these are some properties, 5 properties are required. Uh, about this power spectral density. Okay, I'm going to stop this class.